All right, so today's subject is induction. And to be able to talk about that, I will need to cover some preliminary definitions that relate to the previous lecture. So last time we basically just saw functions and maybe some comments on foundations, but the last thing we saw was functions. So a few additional definitions that we need is if you have a function from x to y, then this function is called injective if it sends different elements in the domain to different elements in the codomain, right? You cannot have repeated elements in the codomain. The contrapositive of the statement that I just said is that if two things get sent to the same object in the codomain, they must have been the same, right? It has a unique pre-image, would be another way of saying it. Similarly, a function is surjective if its image on the entire domain is the entire codomain. So basically every element in Y gets covered by some element in X. We defined this notation last time at the image. And a function is bijective if it satisfies both things. So maybe let's use some abstract examples. Okay. So the main idea is that if this is X, and this is Y, then yeah, the quiz will be this Thursday. There's no quiz today. Thanks for the question. Okay, so something is not injective if it sends two different elements to the same thing, right? So this would be an example of something that is not injective. Let's say that these are different. So this is not injective, right? And if there are things in the codomain, maybe some lone element A, that doesn't get hit by anyone, then this is not surjective. So here's an abstract example of a function that is neither, right? All you need is two elements in each set, and that is enough to produce a function that is neither of those things. If you want an example of something that is injective, then the identity function that we defined last time is always injective. In fact, it is bijective, right? And if you want an example of something that is injective but not generally bijective, then the inclusion mapping that we defined last time satisfies this as long as you have a proper subset, right? Maybe I should write this down. So the inclusion I from 0 to 0, 1 is injective. But not surjective. And if you want an example of a function that is surjective but not injective, you can use the same thing but in reverse, right? You can have any function from the set 0, 1 to the set just containing 0, like the constant function. That would be an example of such a thing, right? So the identity is bijective. Identity is bijective. Always bijective. And the constant from 0, 1 to 0, there's only one constant, right? There's only one way to define a function there, so that's why I'm saying the constant function that does that is surjective. But not injective. Not injective because it sends everything to the same element, right? It's a constant function. Constant functions are generally not injective. Okay, so now you have an example of each, and I think this covers everything. Something that you've probably seen the same. Okay, let me read out the question in the chat. If the domain and codomain have the same size, would injective imply surjective? That's a really good question. The answer is yes, assuming that both sets are finite. If they are not finite, then the answer is no. And we will look at more examples of all of this on Thursday. Thursday will be dedicated to proving more basic properties on functions and induction and stuff. But today I want to get to the core of induction so you can benefit more from the tutorials? So that's a really good question, and the answer is generally no. You could have an injective, non-bijective function between two sets, not only of the same size, but in fact between the same set and itself. It might not be obvious why you can do that, but yeah, that's the answer. It's a good question. Okay, so something that I'm sure most of you are familiar with, if you have two functions, g and f, and they are chained or linked in the sense that the codomain of one of them is the domain of the other, then you can always define the composition of both functions, which would produce a function from the first set to the last set, sort of skipping over the one that's linking these functions together. And it's defined as follows, right? You simply apply g first, and then you apply f. So maybe a sketch of this is in order. And I won't make any particular examples with this because I don't think there's need for that. It's really struggling to do that. But it seems to work. Okay, so okay, there we go. So the idea is you have a set x, and then you have a set y in the middle, and then you have a set z at the end. You have a function g that goes from x to y, and you have a function f that goes from y to z. Then you can always define a function called, FOG. Some textbooks define the order differently. They write it as GOF. I find this easier to understand since the definition is just applying them in the correct order, even though you're writing them backwards, right? So the function that's written to the right is the one that in this picture would be written to the left. That is coincidence. That's just because in English we write left to right. There's nothing mathematical. There's no mathematical reason for this. Completely arbitrary. Okay, so does this make sense? This is how we define the composition of functions. And if you want to practice writing proofs about things that I've mentioned so far, you can try proving that injectivity, surjectivity, and bijectivity are all individually preserved under compositions, meaning what you can see at the bottom of the screen. We will look at more sophisticated examples and how to write proofs using this in lecture 4. But like I said, the priority for today is getting to induction. Okay. Another thing that we can always define for any relation, if you have a relation between two sets, then you can always take the inverse relation, right? A relation is just a set of pairs of the form A comma B. So the inverse relation is just flip all the pairs. And if you flip all of them, what you get is a relation where you have all the pairs of the form B comma A, where A comma B is in the original relation. You can always do this, right? This will always produce a new relation among the sets flipped in the order when you take the product. But of course, if you apply this to a function, which is a particular example of a relation, you might not get a relation, and it's not hard to see why. Now, what I want you to be convinced of is that if the function that you start with is bijective, then the inverse is indeed a function, right? Remember that a function is a relation with two properties. It has to cover the entire domain. So flipping this, it would mean that the inverse would have to have covered the entire codomain. So you need surjectivity. And the second property is that the function needs to unambiguously define where it maps the input to. And if you translate that back to the inverse, it would mean that you would need the inverse to be injective, right? So both of these properties are necessary. And if you want to practice writing, we can also do this on Thursday. I think maybe that would be a good thing to practice, how to prove that something is a function to begin with. So we would show that the inverse of f is a function. And of course, it would actually be in a bijective function, right? Not just a function. The inverse of a bijective function is bijective itself, and the inverse of the inverse is the original function, right? They cancel out. So don't worry too much about this. If this is the first time that you're seeing this, we won't need this for this lecture, and we will cover this in more detail in lecture 4. Now, this is an interesting condition that Yi Yang actually already mentioned in the chat. it's not obvious, right? It doesn't always happen that you can find bijections between sets. Generally, you can only find bijections between sets of the same size when they are finite, and when they are infinite, well, that's how we define what it means to have the same size. So one notation that I want to introduce to you that we won't really use that much now until chapter 4 is that if there is a bijection between two sets, then we will abbreviate this with the symbol, writing the sets within absolute value and setting them equal to each other, which means that they have the same number of elements, right? And there's many synonyms in English that you can use to describe this phenomenon. I don't want to overwhelm you more than necessary with definitions. We will talk about this more, but just so you know that this is something that exists, right? Let me just cover some very basic properties about this symbol that I just defined. And hopefully this sheds some intuition on what this is. So if you look at the bottom of the screen, more than an example, this should perhaps be called a theorem or a proposition. Maybe change that. So a basic property of the symbol having a bijection between two sets is that for any three sets x, y, z, every set has the same number of elements as itself, right? Reflexivity. How would you prove that this is true based on the definitions that I just gave? How would you prove that there exists a bijection between x and, well, x for any set? How would you prove this? You enumerate the set by itself. Okay, yes, that is the correct idea. But if I wanted to do this formally, right as a proof, how do you prove that there exists a bijection? You have to exhibit an example, right? Exactly, the identity function, as I just mentioned before, is a bijective function. It's a bijection from any set to itself. So this proves that there is always at least one bijection from any set to itself. Generally, there will be many, but this is not really important. Now look at property number 2. If x is in bijection with y, then y is in bijection with x. This seems obvious, right? It seems obvious that the order in which you write this shouldn't matter. But something that I would want to point out is that it is not obvious in the sense that, well, this is the equality symbol, so of course that is symmetric. That is not really the equality symbol because I didn't define these symbols individually, right? I am defining this symbol as a whole. So it isn't really that obvious that this should be symmetric. Now I ask you, how would you prove that this is in fact that we have the symmetry? How do you prove that if x is in bijective correspondence with y, then y is the same with respect to x? So this is an if-then statement, right? So to prove this exactly, you assume that there is a bijection from x to y, but then the inverse is a bijection from y to x. It just goes the other way. Okay, perfect. Now, what about number 3? If you've understood it so far, then this shouldn't be that surprising, right? If x has the same number of elements as y, and y has the same number of elements as z, then you can conclude that. How would you do that? Okay, so composition is the correct way to think about it. Now, these wouldn't be identity functions per se, right? But it would be the bijection between x and y, and then the bijection between y and z. And why would the composition be a bijection? Well, I didn't prove it in this lecture, but everything you need is already in these notes, right? In fact, it is an exercise here somewhere. That the composition of bijections is bijective. So of course you would have this. Now, it would seem that we just proved that this symbol that I just introduced to you is reflexive, symmetric, and transitive. And if you remember, I haven't properly defined this, but in the first lecture, I told you what that means, and it will be mentioned, I think, in one of the tutorials, or maybe it was already mentioned last week. It would seem that I just showed you that this is an equivalence relation, and you might think that this is the case, but you'd be wrong. However, it is a very subtle thing, and I I feel like I should postpone explaining why or answering this question until chapter 4, because right now I think it will only cause more confusion. So this certainly behaves like an equivalence relation, but there is one crucial thing in the definition missing. Now, I will leave that as a question to you, also because I haven't, in my notes at least, defined equivalence relation. We will do that on Thursday as well. But this is an interesting thing, so do think about it. And don't get confused. This isn't really that important. Now, why did I bother introducing all of this, talking about this new symbol and bijections and all of that? What does this have to do with the natural numbers? So something that I very ambitiously want for this course is to construct every structure that we will talk about before we work with it. Because, I mean, that's just part of what abstraction means, right? You need to know that, what if an alien race came down to Earth and they were saying, well, we don't really use real numbers, we don't really use fractions, we don't really use rational numbers, we use a different system. But it's interesting that you're talking about this. How can you be sure that this exists? And if you look at my previous lecture, think about my previous lecture, I gave an example of a set that incurred in a paradox. So clearly not anything that I write down in symbols makes sense and actually exists and produce something that we can work with. So when people say, okay, this is, you start a class in calculus and they say, well, we have these 8 axioms that are satisfied by the real numbers, and using this I will define integrals and limits and continuity and all these things, then you might be asking, wait, where did these axioms come from? How can we be sure that they exist, right? That they actually produce something that we can find. And one way to do that is to construct the structure. Now, if you also remember my last lecture, I also told you that we can't do everything from scratch because we have to start somewhere, right? We have to start with some assumption, with something to build on, right? The solid ground that I mentioned with this in the analogy of the horse and all that. If you don't know what I'm talking about, then go back to my previous lecture and I promise it will make sense. Okay, so in this course, I will not be constructing the natural numbers. We have to assume that they already exist. But I will maybe informally discuss how you could construct them if you really wanted to. So here's the idea. If you remember my very first class, I said that an equivalence relation is a way to cut a structure into pieces, right? It's a way to define a partition. So the equivalence relation, quote unquote, because it's not really that, but we can think about it that way, that I just defined and proved to you, can be used to cut up the class or the collection of all finite sets, right? So if we have the collection of all finite sets, whatever finite means, I know I haven't really defined what finite means, I will do that in chapter 4. So this is the collection, the family of all finite sets. Then the thing that I just defined is cutting this into pieces, right? All sets that have size 0 will be in one corner. All sets that have size 1 will be in one corner. All sets that have size 2, and so on, right? Now, of course, we don't know what 0, 1, 2 means, and we don't have to, because the relation that I defined up here doesn't talk about natural numbers at all. It's just a condition on functions. And that's the interesting thing about this. So maybe let me add something else. So of course, the empty set is the only element of this class that has exactly 0 or no elements, right? It's the only one that will be in bijection with itself. Then here, let me make this a little bit bigger so it makes sense. So here, there will be a piece of this huge cake that has this set, right? A set with just one element. That's not the only set with just one element. Also, this one has exactly one element, right? There's exactly one object in between the curly brackets, which is the only element of that set. And we can continue doing this. Of course, this is a very abstract definition, right? But we can add actually any set, any singleton will be in the same class because all of them are in bijection with each other, right? So there's another piece of this huge cake that has exactly 2 elements. And one way that we can construct such a set would be something like this, right? That is a set with exactly 2 elements. Its first element is the empty set, and its second element is that singleton, right? Those are different because one of them is empty and the other one is not. So it has indeed two elements. Now, I know this might seem a little bit abstract, which is why this is all written in green, and which is why I told you I would not be constructing the natural numbers. This is just in case you're curious, this is how you would do it in a more formal sense, right? Exactly. Okay, so Yang, I think, got the right idea. Now, unfortunately, it seems, I need to pause this. Give me 1 second.